Basic definition of flip-flop. What is it?
Stores a bit of data. Storage of
Storage. Why am I writing storage? There we go. Temporary. That's what I'm looking for. Temporary storage. What the hell's going on? Just had a child get all fat and I'm sleeping now. Anybody else sleeping?
Yes, sir.
Device. You can say bit of data because that's what it really boils down to. Data is just a bunch of ones and zeros. Or a bit of data. So 1 or 0, that's your only options. And to include what you can think of as memory function. Same stuff we've already discussed. Just a reminder for review. How many different flip-flops do we look at? 4. There's 4 up there, right? 4. Right, 4! But before we get into the recap and review here of this, you got to remember this stuff. We always deal with our inputs on the left side, outputs on the right. If an input looks like this, what does it require? Requires a, well, that doesn't tell me much.
High input.
How about a high input or a logic
1.
high or 1 as its input? What about this one? Because there is a what? Inverter. Inverter. This will require a logic low. What about these over here?
Up, down, up.
Yeah. This requires positive edge of the clock to do what? Rhymes with transition.
Transition.
Yeah, we're flip-flop to transition or change states. Positive edge. What about this guy? Negative edge. You notice, be sure, people are paying attention for things like this. Our first type of flip-flop, going to SRRS, however you want to say it, depends on textbooks. Now, it's set up different than the lesson, but it shouldn't be a problem. Because I can do this with my magic orange marker. If we remember, every one of you should be able to determine right now what's going on in the flip-flop. Yamamoto!
Yes, sir.
What's up with that?
Well, it needs a logic high.
Okay. To do what? Or as a...
Make it in the middle.
Make it in the middle. In the middle. Inside the flip-flop.
Yes.
Okay.
Inside.
All right. Inside.
It will be R because it's logic 1.
Okay. So R stands for what?
Reset.
Reset. Reset equals, or its function is a logic low, or reset the flip-flop. Set equals what?
1.
Story, logic 1, or set. So, you refer to this chart here, or this legend, this input with no inverter requires a logic high for its function to be active. So if I have a logic low and S, either one of these, there's no inverters, so they would both require a logic 1. So how or what is being stored right now, Mr. Hiromoto?
0.
0. And why? Why is it logic low?
R resets.
Yeah. And R has a, what do we call it? Activating signal, which needs to be a logic high. So if the S function has a logic 0, then it's basically offering it. What's on Q?
0.
Why?
Because that's what
Simple answer, why?
reset.
No, why is Q a 0?
Because that's the output.
Yes. Why is it a 0? You're almost there. That's what's being stored. What's being stored reflects Q's output. That's what I'm looking for. Close enough. What about not Q?
1.
1. And Q and not Q, they are complementary to each other. Complement each other. Now if I throw a curveball, here it comes. Here comes a curveball. Here it comes. Be ready. Be ready. No, it's a curveball. And Mr. Salmon said he wants to answer this one. He told me before chow. When you do the second RS flip-flop example, I would like to answer. Yes. What's going on?
S wouldn't conduct because it needs a low, logic low. And so the reset would conduct again, storing a 0 in the flip-flop.
Okay. You're saying the word conduct, is that?
Yes.
Okay. But you say like active, activated, and all that. So to reiterate what you just stated, this RS flip-flop will be storing a logic 0 given these inputs because set requires a logic low as an activating signal and has a high. Set is inactive. Reset requires a logic high to activate, and it has a logic high. Reset function equals 0. And that's why it's 0 once again. Q's output always reflects what's being stored, not Q's is complement. Amazing. Can we handle that one?
Yes, sir.
Yeah, that's easy. Toggle. Only one input. What's required for this thing to toggle or change states? Go ahead, Mr. Porter.
Clock signal.
Okay. Be more specific, though.
The logic low portion.
Okay. So now, if we got a pulse train or a little clock signal, well, look, I don't know what happened to that one. We got all distorted. I guess. So for this setup, for the toggle, has an inverter. Requires a logic low to change states. So it's only have one input. This is going to go 1, 0, 1, 0, 1, 0, 1, 0. That's all it's going to do with this pulse train. But on every logic low, that's when it's going to change state. So if I have a logic 1 being stored currently, and I say something like 2 clock pulses later, or or 2 activating signals later, what's the output? We'll do, this is what we got. We got this, we got this. So right now, at this moment in time. So 2 later, we could say, or 2 activating signals later, because we know we're waiting on 2 lows. We got a 1. What's going to happen? Next activating signal, 0. Next activating signal, 1. How hard is that? There's no higher level math you got to do, or anything like that. Or do you? No. The output frequency is what relationship to the input?
Half.
Half. Output frequency is half the input. Because as I explained during the lesson, you got a 0 here. So here's 1, okay, bump, 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 bump. Toggle, bump, 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 toggle. So it's got to wait. It has to wait till the next 0 or logic low comes along. So it takes time to do that. Output's going to be half the input. So I do something like this. Here comes a curveball. Here's a curveball. No, I won't do that. I won't do that to you. Storing a logic 0. 6 activating signals later, what's going to transition to? Okay, logic low here, low, 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 trip. Low. 6 later. Logic low. There's a low now. So really all you got to say to yourself is high, low, high, low, high, low. See? That's